So we've achieved high quality electronics by organizing and working with the lowest length of wires needed. The breadboard is therefore very clean, which is optimal for working conditions and debugging. We've chosen to elevate the main electronic component by gluing a cardboard plate on the box and zip tying the loose wires onto the cardboard box, eliminating all risks posed by possible water spilling. Furthermore, we have many double layer concepts with the styrofoam box and the OD sensor shoe box to remove the water risk. We ended up using 2 pumps, since this would be the best solution for temperature control. We still have a siphon from the mussel bucket to the algae bucket, which removes 1 pump from the system. We've added code fail-safes. If a sensor fails or a value goes off, the system shuts down the peltier and both pumps to prevent overcooling or overfeeding. We also cool the voltage regulator by zip tying it to the peltier. While this slightly reduces cooling efficiency, it improves overall safety and reliability. So in terms of our PID controller, we pump water out of the mussel bucket into the peltier cooler and back into the mussel bucket. Our PID controller outputs a value between 0 and 100, and this is interpreted as a percentage of maximum power for the pump and converted into PWM parameters, as a higher flow rate results in more cooling. When we run the PID, we get a net reading of 17 degrees, which is our set target. Our PID coefficients are tuned such that we initially have water at around 20 degrees. We have decent stability considering the low steady state error and maximum overshoot. Some factors in the stability is the styrofoam insulation and by clamping the integral to combat windup. On our web server, we have decided to monitor algae concentration and temperature, while we also have sliders where we can change the individual coefficients of the PID controller. For our storage and export of experimental parameters, we initiate a CSV file with the headers seen here. At the end of every loop, we write the relevant variables in the CSV file. We can also see or retrieve data from the Adafruit dashboard if we wish. So the concept of the OD sensor works, however calibration is a bit off and reaching the low concentrations remains a bit difficult. So far we've seen a cutoff detection value of around 16,000 cells per milliliter, where the tested values of 8,000 and 4,000 and 2,000 can't really be told apart. We could use a larger length of water from LED to sensor to create a high sensitivity for the lower concentrations. Problems with the relay frying meant we had no time to do the planned final OD calibration. And our plot can be seen here with our error bars. So for the mathematical model, we first look at the differential equation for the algae bucket. We have the equation for the light-dependent growth rate, which is limited by the crowding factor based on the algae concentrations. We get this total equation. And for the mussel bucket, we have the mussel filtration, which is based off of water temperature and is also dependent on algae concentration. So the equation formed is the algae input rate minus the mussel filtration rate. For the ODE, optimized with a pump rate and duty cycle to keep the mussel bucket at 2000 cells per milliliter, which is considered ideal. And then we have our starting parameters here on the right. Our results show that the model keeps the mussel bucket at 2000 cells per milliliter, which is ideal. The algae population grows and therefore we pump less to mussels as the concentration grows to keep the algae input equal to the mussel filtration. We also have a low PWM for the pump, which is very energy efficient. So in terms of our innovation and sustainability, after conducting calculations, we see a significantly lower energy consumption by eliminating one of the pumps. This results in us saving around 13.14 kilowatt hours per year. Furthermore, we have chosen a lot of sustainable choices in terms of material use. We've only reused materials to repurpose it. This is eliminating the use of 3D printing, saving approximately 60 to 100 grams of PLA plastic, which we would have used for the OD sensor. This is also better for the biocompatibility, since the buckets and the lab are made of the same materials as our OD sensor container and is therefore known to be biocompatible based on the lab tests. The choice of reusing a styrofoam food insulator box as our insulator showed great results due to its insulating properties. We saw that the temperature of a body of water would increase at a lower rate in the box after conducting the experiment where we measured its efficiency. Finally, we used hardware hacking to cool one of our electronic components by attaching it to our cooler. We were able to observe much less heat on our component, which allows for longer running times, as we previously experienced failure in our component due to overheating. So some things we'd like to highlight was the characterization of the pumps, which can be seen right here where we plotted the performance of each of the 2 pumps. The growth rate of our algae in seawater was determined to be 1.39 times 10 to the minus 6 cells per second, and for the medium it was 1.74 times 10 to the minus 5 cells per second. This was determined with the data we presented last week and the formula on the right here. The mussel clearance / feeding rate was determined to be 2.32 liters an hour. Finally, we wanted to highlight that one of the most important findings from the lab was that exposing the algae just to the sun would actually be sufficient for their growth and would eliminate one more user, which was the LED. However, this wasn't possible in the makerspace.